Hi there, pre-calculus students. This is Mrs. Brunk, and welcome to class. Actually, welcome to our very first class together. And it won't be our first day together because, as you know very well, there was some content that was sent out to be done as summer homework. And so we've already covered a few of the introductory topics. And we've even had a quiz to be sure that you've mastered those topics. So we wanted you to make sure you have some basic skills or remember some basic skills from Algebra 2 so that we can hit the ground running. And that's actually what we intend to do today, is to jump right into algebraic expressions to where the summer homework left off, which is on special product formulas. So before we jump into that, though, I do want to talk a little bit about the structures of the lesson videos and the expectations for you as an active participant in class. So first of all, because this is a college level class, the expectation is that you will be doing most of the note taking yourself. And there may be some basic structure provided to you, some sort of general notes that will be given to you, as is done in most college courses. In fact, my daughter is in a calculus class currently in college, and they do give her a course pack, but it is pretty sparse, and it's going to look a lot different than maybe note packets you've had for other classes in math. And basically it's sort of a skeleton of, notes, and it's basically gives you a little format to create your notes. And then there will be some times where we may not have that structure note packet, and the expectation will be that you're taking your own notes in a notebook. So, the nice thing about having the videos is if you are kind of a slow note taker, first of all, the practice you'll get quicker at it, and that's going to be really important when you're doing live lessons, and especially at the college level. And but the nice thing about the videos is you can pause the video and catch up on notes, rewind if you need to. So that I definitely think will be an asset. So the expectation is that you have these notes that you're going to use as your study tool, especially because we won't cover everything in every lesson. And so this will help you to focus on exactly what's important from the lessons by what we cover in our lesson videos. So I'm really looking forward to being with you this year. I'm looking forward to kind of helping you build your portfolio of math and kind of to get you to that point where you feel really empowered to take on any challenges that you have at the next level, college level, for math courses. Or if maybe you still have some time left here in high school and you're considering taking AP calculus, or possibly AP probability and statistics, although we don't really do a whole lot with that in this course, but just the being able to handle a math class of this level is certainly important and will undoubtedly serve you well in your future. Okay, so we're going to jump right into our very first topic. And our first topic, of course, is from Lesson 1-3. We're picking up where we left off from summer work. And we're going to be looking at what are called special product formulas. Now, most likely you'll have some sort of general sort of skeletal notes, as we talked about. So like a course pack kind of thing. And it'll look something like this probably. And you're just going to be filling in the things that we cover in class. So what do we mean by a special product formula? So a special product formula is basically a product of things that come up quite often, And it's a formula, so you remember that formulas are, we've seen formulas that will allow us to save us some time, like for instance, the quadratic formula. That is something that's used to save us time. It's sort of a recognition of a pattern that we can then apply moving forward. And that's exactly what these are. These are formulas for multiplying 2 binomials or 3 binomials in a way that makes it very quick and improves your accuracy down the road. And so the expectation is that going forward, if, for instance, I ask you to say square a binomial like here, like this one, square A plus B, you will be able to do this without really showing any work. And I know that's kind of unusual. As a rule, math teachers usually want you to show all your work. And of course, that is the case usually in here. But for special formulas, we want you to have these things memorized. And in fact, you will have a quiz where you'll have to demonstrate that you have memorized these formulas. So the first one is, I'm not sure if the label is accurate here on this, but this is what it says in the book: sum and product of same terms. I think it's supposed to be sum and difference of the same terms. So I think that's what it's supposed to be. And I mean, I know that's what it is. So I just think that's a mislabel there. So hopefully we'll see that maybe that was just a labeling error there. And so if you look at the 2 binomials we're multiplying, they look almost identical except for one is a sum and one is a difference. And so, typically if we were multiplying something like this, and we didn't notice that they had the same terms in the binomials, but just one was a plus and one was a minus, we would actually FOIL them out. So if we were to do that, and again, this is what we really don't want to be doing going forward, but if we did, this is what it would look like. Remember, we'd say first, outside, inside's last, so we multiply the first 2, which would be a squared, the outside 2, which would be plus AB, the inside 2, which would be minus AB, which, because, it's a minus B and a positive A. And then the last 2, which would be a negative, because one's positive and one's negative, a negative B squared. Well, because those 2 terms in the middle are opposites, they cancel out, and it just leaves us with A squared minus B squared. And so going forward, if we see anything like this, so if we see 2 binomials that are identical except for the sign, one's plus and one minus, what we'll be able to do is just get that product by squaring the first term and squaring the last term and then subtracting. So it would just be A squared minus B squared. So again, going forward, we won't want to have to show this work. We just want to, but this is just to kind of show you why this works. So that was number 1. Number 2 is A plus B squared. Now, this is a very common mistake. People want to say that when they see this, a binomial square, they just want to square both terms. And they want to say this is A squared plus B squared. Okay, well, that's not correct. So we definitely want to make sure we understand this one, because that's a very commonly made mistake. Because remember, what that really means is we have to multiply the whole binomial by itself, meaning we have to take the 2 terms in the first binomial, multiply it by the 2 terms in the second binomial, which is going to give us 4 terms that may or may not be able to be simplified. So if we FOIL to take the first 2, A times A is A squared. Outside 2 would be A times B, which is AB. The inside 2 are B times A, which is again AB. And the last 2, B times B, which is B squared. Well, this time the middle terms do not cancel. There's 2 of them. And so it turns out that it's A squared plus 2 of these AB terms plus B squared. And that's actually the formula that we want to remember. And this is how we can do this without actually doing FOIL, is we can look at, and let's write this in, A squared plus 2AB plus B squared. And basically how it works is this. It's you square the first term, and that's where that comes from. You square the last term, and that's where that last term comes from. And the middle term is 2 times the product of the two terms. So it's twice the product. So when we go through and we see a binomial square, we can just square the first term. We can square the last term to get the last term. And we can multiply the two terms and double it to get the middle term. So that's called the square of a sum, or a binomial squared. Now, the only difference between number 2 and number 3 is that, notice that says a minus b squared. So the difference there is that when we square the first term, that would be a squared. We square the last term, that would be plus b squared. But then when we multiply these two and double it, well, one of the terms is negative. So it would be a times negative b, which would be negative ab, and then double that would be minus 2ab. So the only thing that will change there is the sign of the middle term will then be a subtraction. And you may remember these patterns from when we studied perfect square trinomials in Algebra 2 and when we worked with what's called completing the square, right? We were trying to create one of these square binomials, and it was a method that we used to solve quadratic equations, right? Or to put something that's a quadratic equation into vertex form, right? So the final two have to do with taking a binomial and cubing it. Now, that, as far as that goes, like to do that algebraically and without using a formula, is a little more elaborate and definitely can cause more problems down the road because of just chances to miss terms or make errors. So I'm going to show you this one time, and then I'm going to kind of remind you of maybe some ways that we did this and we had shortcuts in Algebra 2. So I'll just do the first one, a plus b cubed. And what that really means is a plus b times a plus b times a plus b. And because you have three things, you can't multiply three things at a time. And so what we always do is we'll take two at a time. So let's say maybe I took the last two and multiply those. And then whatever I get, I can multiply it by another a plus b. So I'm going to put this first a plus b, and then I'm going to use what I just learned about squaring a binomial, because now what I've done is I've changed this to basically say a plus b times a plus b squared, because I have two of them now. So when I multiply these out, I'm going to end up with a squared plus 2ab plus b squared, right? And so then to get to that final product, now I'm going to take each of these terms and distribute it through, and then I'm going to combine any like terms, right? So a times a squared is a cubed. A times 2ab is plus 2a squared b. A times b squared is ab squared. And then I'm going to distribute the b through, so that's plus a squared b. And again, you always put these in alphabetical order. That way you'll recognize if you have like terms. And then the b to the second term would be plus 2ab squared. And then finally the b times the b squared is plus b cubed. So that's, again, you can see a lot of work that involved in that. And then we can put our like terms together. So there's only one a cubed term, right? So that's done. And then there's an a squared b term there and an a squared b term there. And there's really a 1 in front of this one. So that makes a total of 3 a squared b plus, okay, so those are done. And now there's these ab squared terms, and there's 1 here, and there's 2 there. So there's a total of 3 ab squareds. And then finally, so I've used those up. Those are done. And all that's left then is the b cubed. Now the order doesn't really matter, but this is kind of the natural order that they came in as I was doing my distributive property. Now what you might notice, and especially if I put the coefficients in on these that have a 1 coefficient, which we don't typically do, is you see the series of numbers as coefficients 1, 3, 3, 1. Now you may remember that that's actually one of the lines from Pascal's triangle. So Pascal's triangle looked like this. It started off with a triangle of ones, and then it went like this: 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. And basically, it's each of the lines, each new row was created by adding the 2 numbers above it. So like, for instance, in row 3 here, this first term 1, what comes from adding the 2 numbers above it to the right and to the left, which there is no number to the left, so that's really like a 0, right? And so when we add those 2 together, we get 1. When we add these 2 together, we get 3. When we add these 2 together, we get 3, and so on. And so basically what we learned is this thing called binomial expansion, and it was a shortcut where we could take the line from Pascal's triangle, so that was associated with the exponent. So of course, if we have the exponent here is a 3, so we'd get line 3, which is the 1, 3, 3, 1. And that would actually represent the coefficients of the terms that we're going to have in our final product. And then essentially what we would do is we would take the first term and we'd start at that power, which is 3, and we'd work our way down. So that would be a cubed, a squared, a to the first, and then a to the 0 power, which is just 1. And so that's really like putting another times 1 there, which really isn't doing anything there, right? So then what we would do is we would take the last term and we'd start at the 0 exponent and we'd work our way up. So we'd say b to the 0 power, which is really 1. So that really is unnecessary. It's not changing anything. And then b to the first, b to the second, and b to the third, right? We'd work our way up for the second term. And then all of the signs would, in this case, because that's a plus, they would all be positive. Okay. And that was a special way, and some of you may have used a table way. I know, I teach a table way, which I think is helpful. But once you kind of get the hang of it, you kind of maybe just can use the regular Pascal's triangle way to do this. Let me see if I can fix that a little bit. And there we go. And you can see that we get the exact same thing that we got from doing all this work, right? So essentially what you do is you take that 1, 3, 3, 1 from Pascal's triangle. Those will be the initial coefficients. And then you just take the first term, start at that highest power of 3 and work your way down, and start with the second term at the 0 power and work your way up to 3. And then if there's any simplifying to do, you can do that. So that is the cube of a sum, and the cube of a difference will look identical to this as far as the 1a cubed 3a squared b. So it's basically working your way up from one, or down for one of the terms and way up for the other, and then including these coefficients. And then 3ab squared and then b cubed. And then again, you don't really need to have these ones in there if you don't want. They're just sort of, just a reminder that is the coefficient. But the difference here now is the signs will alternate minus, plus, minus. So the minus and then plus and then a minus. So these are the special product formulas that you are expected to know by heart. And you'll kind of get the hang of these once you get some practice. So that's how we're going to wrap up our lesson today, is we're going to get some practice using these and also look at why this works with other more complicated looking binomials. So the key idea in using these formulas, or really any other formula in algebra, is the principle of substitution. And we may substitute any algebraic expression for any letter in a formula. For example, to find x squared plus y cubed squared, which was basically that sum of a square, or square of a sum, which is formula 2. Instead of using like a and b, we'll use x squared and y cubed instead. And so, for instance, again, if we want to expand this out, see what I'm saying is we pretend like x squared is like the a and y cubed is like the b. And so remember how we did that expansion is we would square the first term. And so what we're really doing is taking x squared and squaring it, which means that's really x to the 4th, right? And then we're taking the last term and we're squaring it, which would mean that we're taking y cubed and squaring it. So that means we'd end with y to the 6th. And then we take the two terms and multiply them and then double it. So we 2 times the product of those two terms. So if we took x squared and multiply it by y cubed, we'd get x squared y cubed, and then double it would be plus 2x squared y cubed. So again, as the terms in the binomials get more complicated, we can just use this idea of the principle of substitution. So let's see if we can practice our special product formulas with these examples. So for A, we want to square 3x plus 5 squared. And again, without actually doing FOIL. So what we're going to do is first take the 3x and we're going to square it, which means we're going to square the 3 and we're going to square the x, which is 9x squared. And now we're going to take the 5 and we're going to square it to get the last term. So square the 5 and we get 25. And then multiply the two terms. And again, that's a positive 25 because we're squaring positive 5, right? And then we multiply the two terms and then double it. So 3x times 5 is 15x. And double it, that makes 30x. And there's our expanded version of that. So 9x squared plus 30x plus 25. Now, some people like to do it sort of in order instead of doing like the first, then the last, then the middle. So if you want to, that's fine. Just square the first, then multiply the two terms and double it to get the middle term, and then square the last. However you decide you want to look at it, you'll still get the same product using that formula. Okay, let's try another one, B. So this time, it's a difference of cubes. So we have x squared minus 2, and we want to cube it. Okay, so remember how that worked is we'd first start off with these coefficients of 1, 3, 3, 1. And you may even want you may even want to put the signs in. Because if this is a subtraction, we know that they're going to alternate starting with negative. So it'll be minus, plus, minus, right? Oops, I don't know if I left enough space there. Minus. And then what we're going to do is start with the first term and we're going to raise it to the 3rd power and work our way down, right? So it's x squared to the 3rd power, which is x to the 6th, right? And then the next one would be x squared squared, or to the 2nd power, which would be x to the 4th. And then x squared to the 1st power, which would be x squared, and then to the 0 power, which would just be 1. Okay, so there's really like just a kind of a 1 there, which again is really unnecessary to put there. And then we're going to take the second term, this term, and we're going to start at the 0 power and work our way up. Now you can kind of think about this as just the 2, and you're applying the powers to because you've taken care of the signs. Or if you haven't taken care of the signs, you can kind of think about that as a negative 2 and raising it to different powers. So when you take a negative number and raise it to odd powers, of course, that would be negative. So if you don't want to have to worry about memorizing like that these are alternating signs for the difference, you can do it that way. You can kind of think about this as negative 2 instead. And it'll all work itself out. So anyway, so the first thing I'm going to do is I'm going to raise -2 to the 0 power, or just 2, I guess, to the 0 power, because I already have the signs in, and that's just a 1, right? So I don't have to put anything there. And then I'm going to put, I'm going to raise it to the first power, which is times 2, right? I got to leave a little more space here. I'm sorry, I'm not very good with spacing here. So times 2, and then to the second power, which is times 4, and then to the third power, which is times 8, right? So then we simplify. So that would be x to the 6th, and then the 3 times the 2 is 6, so that's minus 6x to the 4th. And then 3 times 4 is 12, so that's plus 12x squared, and then minus 8. And that's my expanded version. That's my answer, right? So with those, you might show a little bit of work as you're expanding them out, because eventually you might have to like multiply those coefficients from Pascal's triangle by some other values in your, that come from the expressions in your binomials. So. Now, another one of our special product formulas was the one where we had 2 binomials that were nearly identical. Just one was a minus and one was a plus, right? So remember in that one, the middle terms canceled out because they were opposite signs. Well, that's what we have here in example A. So in order to use our special formula here, we know that all we really need to do is multiply the first 2 terms, right? Which would be 4x squared. And then multiply the last 2 terms, which are negative y squared and negative square root of y and positive square root of y, which would be minus y. And again, remember the middle terms are going to be opposites, so they'll just cancel anyway. So here we go, and that's our answer. Now, B looks maybe like something that we haven't looked at. It doesn't look like any of our special patterns. But in fact, if we use this idea of substitution and maybe grouping, we might see that we actually do have one of these special patterns, because we could look at it like, a couple different ways. We could group these 2 things together and say that's one term. So this would be like our A, and then we could make these be the B's. Or alternatively, we could look at it like these 2 are our B's and these 2 are our A's. You're going to end up with the same answer. I personally think this way is a little easier, and the reason why I see that is that if you look at multiplying the 2 B's, one is y minus 1 and one's y plus 1, and that's like this special pattern that we just looked at over here. That's the where the 2 binomials are nearly identical, but one's minus and one's plus, and those middle terms are going to cancel out. So that's the one I'm going to do. So so that's the thing, and then this is a plus kind of thing, right? And I guess, I don't know, maybe now that I think about it, maybe I'm kind of thinking maybe going the alternate way. Yeah, I think I'm going to go the other way. And I just saw something different. So, we learn as we go along. What I actually see now is that this is a minus and this is a plus. So if instead we did the groupings like this, like these were A and these were B, it makes it one of these differences, where the one's a difference and one's a sum. And we don't have to worry about middle terms. So that's what we'll do instead. So we'll take the A times the A. So we're going to multiply those 2 things. And so when I'm multiplying A plus Y, so it's really like X plus Y times X plus Y, it's really X plus Y squared, right? And then I'm going to be multiplying the 1 plus 1, which that's easy. So that's minus and a plus, which makes a minus, and 1 times 1 is 1. So really all I have to do, expand this out using my square of a binomial, which is going to be x squared plus 2xy plus y squared, and then we have that minus 1. Now that one seemed a little bit trickier, and so I want to just help you to verify that in fact that is the correct answer. And so what I'm going to do is going to do the long method, which again we want to get away from, but just to verify here, so you know that you can trust these patterns, is I'm going to do the old school way of distributing, and I'm going to show you that we get the exact same answer as what we've said is the correct answer here. And again, the order that we write these really doesn't matter. So I usually just leave them in the order that they come up. So if this was just a single variable, though, you would want to put them in descending order of powers. Like if you just had x's, you want to start with the highest power and work your way down. But when you have x's and y's, you might be putting one in descending order, but then what are you doing with the other? So there really is no specific order those should be in. So anyway, I'm going to do the distributing. So if I take the x and I distribute it through, I'm going to have x times x, which is x squared, x times y, which is xy, and x times 1, which is x. Next, I'm going to distribute the y through. Okay, so y times x is xy, y times y is y squared, and y times 1 is y. And then I'm going to distribute the -1 through. So -1 times x is minus x, -1 times y is minus y, and -1 times 1 is minus 1. And then we're going to go ahead and put our like terms together. So are there any other x squared terms? Nope. X squared, that's done. XY and XY. Okay, there's two of them, 2XY. Are there any other x terms? Yep, there's a minus x. Well, look, those cancel each other out. So they're gone. Next, is there any other y squared terms? Nope. Y squared, so that's done. There's a y and a negative y. So again, those cancel each other out. And then we're down to the -1, and there's no other term to go with that. So that's exactly what we got by using one of our special product rules. And that's actually all we're going to take on for today's lesson. So what you want to make sure you're doing is, as you're completing problems that are based on this, you are following these special product formulas, and that you're memorizing these. Now, I guess I don't know if I want to necessarily say memorize. I'm not a big advocate of memorizing. It's really more just understanding the pattern, how that works. And pretty soon it'll become second nature to you. Students in my Honors Algebra 2 class always say, well, how do you, wait, I don't know where that just came from. Like I'll see a binomial and I'll just write what the, expanded version is out. And they don't understand like where that came from. And I say, oh, I'm sorry, I forgot. Like we don't know those special rules or patterns yet. But those are always things that I'm applying to just make my life easier. And also you can see that when you do these algebraic manipulations, you're doing these distributive properties and whatever, there's so many opportunities to make errors. So by knowing and using these formulas, you not only save time, but become more accurate. So that's our goal for today. And thanks for coming to our first pre-calculus class together. And good luck to you. I'll see you soon.